Hey everybody, this is your first video in the series of videos for Unit 5, which is probability. So I'm going to split this into two different sections. The first section is probability basics and working mostly with two-way tables. And then the second section is about probability distributions when we're talking about variables. Okay, so this video is just an intro to probability. I'm going to talk about a couple of rules and laws, and then I'm going to show you how we use simulations to calculate probabilities, which you've actually been doing since the beginning of the year. You just didn't realize that you were doing it. Okay, so let's jump into it here. So first question is, what is probability? What is that? What does it mean? Okay, so a probability is any number, so it's a number between 0 and 1 that describes the proportion of times an outcome will occur in a long series of repetitions. If I could spell, that would be great. Okay, that is our very fanciful statistical definition, right? But I think we understand inherently what probability is. It's how likely something is to occur, right? And the way that that is calculated often is you do the same thing over and over and over and over again. That's your long series of repetitions, right? And we then use that in order to figure out how many times a certain thing occurred um, after doing something over and over and over again, or asking the same question to lots of different people, right? And getting their responses, things like that. Okay. So there's a couple of laws about probability that you need to have a general understanding of. It's not usually explicitly asked about, but it's important to know what these are. Okay, so the first is the law of large numbers, okay, which says if we observe more and more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. And that single value is the true probability of a certain outcome occurring in those long series of repetitions, right? The way that that is notated and the way that we notate probability notation is P, capital P, parentheses, and then you put the event that you are concerned with finding the probability for inside parentheses. So if you see P parentheses A, that means probability of an event A. Right? So the law of large numbers, the way I kind of want you to think about it is if you take say you flip a coin, right? You flip a coin and it's a fair coin. So you have a 50-50 shot of landing on heads or tails. Okay. That 50-50 shot comes from the law of large numbers. Okay. If you say flip that coin 10 times, right? You could, in those 10 times, have 6 heads and 4 tails, right? That doesn't mean that the probability of getting heads is now 60%, right? It just means in that small sample that we had more heads than tails, right? But if we do thousands and thousands and thousands and thousands of coin flips, eventually the number of heads and the number of tails will even out so that you get 50% of each. Okay. Now, this leads into something that we call the law of averages, and it's a myth that people use, right? So I don't know if you've ever seen on TV or if you've watched like your parents or older siblings, like if you've gone into a casino and watched them gamble, if they've lost a lot, sometimes people will think, well, I'm due for a win, right? But uh, basically insinuating that the probability that they're going to win has changed, but it hasn't, right? So the law of averages tells us the probability of a random event will even out to a specific single value, a true value in the long run, right? That's your many, many, many repetitions, right? But future outcomes are not affected by past behavior. Okay, meaning if you lost, you're playing a round of cards, right? And you lost the last 5 or 6 or 7 rounds, that doesn't mean that your probability of winning in the eighth round has increased at all. It's still exactly the same. Okay, so past outcomes are not going to influence the likelihood of any events that are occurring in the future. Okay, but people use that idea um, to justify certain things, especially when they're playing games of chance, right? They think I'm due for a win, but the math and the law of averages does not actually support that. That in the long run it'll even out, but that doesn't necessarily mean it will even out in the next iteration of that event. Okay, I'm not actually going to do this activity here, but you can if you want to. So the link is tinyurl.com/coinlawnum. Okay, and you can play around with this and record the probability of heads for these number of tosses. If you do it, what I'm hoping you'll see is that as you increase the total number of tosses, that the probability got closer or gets closer to 0.5 or 50%, which is the true probability of getting heads. Okay. And then I ask here, what do you think happens if you change the probability of landing on heads to a different number? Well, then the probability will approach that new value rather than approaching 0.5 as the number of tosses increases. Okay, so those are just some basics about probability. Okay, and the next thing I'm going to talk to you about and tell you about in this video is simulations. Now, you actually, like I said at the beginning of the video, have kind of been doing this for a while, and you may just not have realized that you've been doing it, right? When I ask you to go out and take a sample of something, and then we would put all of those samples together, right? Or maybe I would have you roll a pair of dice to simulate an outcome occurring, or flip a coin to simulate something occurring, or pull a number out of a hat, and a lot of the Desmos activities that we've looked at have had computers running simulations for us. Okay, so flipping a coin, online applets are examples of simulations. A simulation is just an imitation of a chance behavior. Okay, now every once in a while, there will be a free response question that comes up on the AP test that asks you to run a simulation. Okay, so I have these steps here that you can use, but really your general process whenever you are asked to run a simulation is to assign numbers to the different outcomes that are possible, to various outcomes, and use a random number generator or random digit table to figure out how likely a certain outcome is just due to random chance. Okay, right, that's what the random number generator and the random digit table do for us. Okay, if you're using your calculator, I have a calculator path for you that will generate random numbers for you. Menu, probability, random, integer, and then you're looking for randint. Okay, RANDINT. That means random integer. Okay, so I have an example for you here. Okay, so I don't know if you all ever, when you were little, would buy cereals because they would put prizes and stuff in the cereal boxes, or they used to put different collectors cards and little trinket things in cereal boxes. So in this example here, this breakfast cereal company is putting NASCAR driver cards, almost like baseball cards, but for NASCAR drivers, in their different in all of their different boxes of cereal, right? And they're saying that it's equally likely to get each of these 5 cards for these 5 NASCAR drivers. Okay. And so somebody decided they wanted to buy up all the boxes until they had all the cards. And when she did that, she had to buy 23 boxes to get a full set of cards. Okay. And so we're going to use a simulation to figure out, is that a rare result or not? Okay. Because we don't want to actually have to go out and buy multiple boxes of cereal. Right. So what we're going to do is set up a simulation with the information that they gave us and see how, just using a random number generator, how likely is it, or how many boxes does it take for us to get all 5 cards, to see if this result that this person got was rare or not, right? Okay, so what we're actually trying to find here is, what's the probability that it'll take 23 or more boxes to get a full set of these collector cards. Okay, so we need to have 5 numbers because we're going to use a random digit table or a random number generator. So we're going to have 5 numbers to represent the 5 cards, right? So those 5 numbers, right, are on the screen here, and they correspond to each of these NASCAR drivers, right? So when we use a random number generator, if the first number that's spit out of the calculator is a 2, then that means we have the Dale Earnhardt card. Okay, then if it spits out a 5, next we would have the Jimmy Johnson card. Then if it spit out another 2, right, we've now bought essentially 3 boxes, right? We've bought 3 boxes of cereal, and I only have the Dale Earnhardt card and the Jimmy Johnson card because I've got a duplicate, right? And I'm kind of going to discard the duplicates, right? I don't really care. I just want one of each, okay? Right? So we're going to use a random number generator here to generate random integers from 1 to 5, right? Where each number represents a unique card, okay? We want the full set of cards. So we're just going to keep generating random numbers until we get all 5 of those numbers, 1, 2, 3, 4, and 5. And then we have to record how many random numbers did we have to generate in order for that to happen, in order for us to have a success, right? In order for us to get all 5 cards, right? So if we are able to do that and not buy a bunch of boxes, right? Quote unquote, buy a bunch of boxes, then this result that this person got actually would be surprising if it took us 23 boxes. Okay. So I did the random number generation and it's here on the screen. So in this first trial, right, my first random number was a 3, then a 5, then a 2, then a 1, and then I have a bunch of repeat numbers, and then I finally get a 4. So there's 9 numbers here, so I had to buy 9 boxes of cereal in order to get my full set. So that's a trial of our simulation, okay? Then we're going to do it again. Continue generating random numbers. I have a lot more duplicates this time, but I'm able to get at least one instance of all of my numbers in 16 boxes. So that's trial number 2. So this was trial 1, trial 2, right? And then I have trial 3, 4, and 5 here. I could have kept going, but I stopped after doing 5 trials, right? So in the third trial, it took me 10 tries to get the result I wanted. Took me 15 in the 4th trial, and then by the 5th trial, it took me 22 tries, right? So based on this simulation, we never had to buy more than 23 boxes, right? That's what we were trying to figure out. What's the probability that it will take 23 or more boxes? Well, from this, that probability is 0 out of 5, right? Because we ran 5 trials and 0 of them, it took us more than 23 boxes to get the full set of cards, right? So we would say that this fan should be surprised because this probability is really, really low. Okay. So I have another example for you here with a frog sitting in the middle of a board, right? this is like, it's like a computer game, right? So he's sitting in the middle of a board. Okay, every 10 seconds, he's going to jump one square left or one square right at random. Okay, and we want to figure out or estimate the probability that he jumps off the board in 60 seconds or less. Okay, so for example, right, if he jumped left, 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 right, that was 30 seconds, right? He made 3 jumps, 30 seconds, and he's off the board. Okay, but if he jumped, let's say, left, then right, so that's 20 seconds, then right again, 30 seconds, right again, 40 seconds, and then he jumped left, 50 seconds, and then right again, that's 60 seconds, and he's still on the board. Okay, so in the first example that I gave you, that would count as a success, meaning he jumped off the board, right? This second example that's up here on the screen now would be a failure because he's still on the board. Okay, so what we're going to do here is describe how we could use this random digit table in order to simulate this idea and estimate the probability. So since he's only jumping left or right, and I have even and odd numbers here, I'm going to say that my left jumps will be represented by odd numbers. Okay, and then my right jumps would be represented by even numbers. Okay, so then what I'm going to do is I'm just going to pick any row on the random digit table. So I started at line 101 here. Right? So I'm going to pick a row on the random digit table and count how many jumps it takes for the frog to go off the board. Okay, right, then the probability of jumping off the board in 60 seconds or less is the number of successful, I'm really struggling with my spelling today, y'all. Simulations divided by the total number of trials run. Okay, so because remember, probability is number of successes or number of people in a category, right? Whatever it is, divided by the total. Okay, so let me clear this off on this side. Okay, so, oops, sorry. Okay, so I'm gonna do 10 repetitions here. Okay, and I'm actually gonna move this over a little bit and zoom in on this side so that you all can see this a little bit better. Okay, so I'm gonna do 10 repetitions using this random digit table. Okay, right? So really, I just need to count the first 6 digits that I see, right? Because that represents the first 60 seconds, right? And so we're going to see if he's still on the board or not. Okay, so I'm going to start with line 101. Okay, actually, I'm going to draw a little line here. Okay, so I'm going to start with line 101. The first 6 digits of line 101 are right here. Whoops. Okay, the first 6 digits are right here. Okay, so on line 101, I have 192239. Okay, so I'm gonna go left. Is he jumping left or is he jumping right? Okay, so remember the odd numbers were left jumps. So here he went left, left. He's still on the board. Right, right, left, left. Okay, so he jumped, right? If you look at, if we look up at him here, he went left, left, right, right. Oops, sorry, hold on. Okay, sorry about that. So he went left, left, right, right, left, left. So after 60 seconds, he's here in this space and still on the board. Okay, so he's still on the board. Okay, let's I'm going to pick a different line now and show you one where he wouldn't end up on the board. Okay, so I'll just tell you, because I've run this simulation already, that line 102 and line 103 also end with him still on the board. Okay, but line 104 is going to turn out a little bit differently for us. Okay, so line 104, the first 6 digits are right here. Okay, so in my simulation, so it's 527113. Okay, so he went left, right, left, 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 left. Okay, so if we go up to our board, right, in this trial, he went left, right, left, 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 left. Okay, so there's his 6 jumps, his 60 seconds. He's way over here now, right? And he's fallen off the board. Okay, so, right, in this simulation, he's off the board, and he's actually off the board in 50 seconds. Okay, so I'll let you know if you want to practice running the extra simulations, okay, and doing this with the 6 remaining lines, you can. I'm going to pause the video quickly and fill in the rest of the data, and then I'll show you how to calculate the actual probability. All right, folks, so here's the rest of the simulations worked out, okay? So if we look at how many times he fell off the board, okay, he fell off the board once, twice, 3, 4, 5 times, okay? So he fell off the board in 5 out of 10 simulations. So we would estimate that the probability that the frog falls off the board is 5 out of 10. Right? Because we ran 10 simulations, and in 5 of them, he fell off the board. So based on our simulation, there's about a 50% chance that that the frog will fall off the board, right? Which kind of makes sense if you think about the actual game, because he's always in the middle, right? And you have an even chance of jumping left or right. Okay, and so that is it for this video. In the next one, we're going to talk about some basic probability rules like the addition rule, complements, all of that fun stuff, right? So I'll see y'all in the next one. Bye, everybody.